We can't hear you.
Hi, yes. So, yeah, I'm just gonna go ahead and start. Talk about designing programming languages. Here's some basic organizational stuff, which is not so important because there's only 3 people. But so yeah, basically the plan is to talk about each little topic for like a few weeks or a couple weeks, and then talk about other just random cool things interspersed in between, so that if you want to jump in at whatever point, you can just jump back in. Yeah. So programming language design. So before we talk, so basically, yeah, we're gonna talk about how you design programming languages. I'm gonna start by saying that programming language design is not like a super empirical science, so to speak. And there's lots of things that we know, but mostly we don't have a lot of data for actually what makes languages good, which is unfortunate. So for example, there's some studies that show that basically a lot of the common languages, like the C-style languages, have just awful syntax. So one study found, so Perl is this language, it's the one here in the middle, it's the one that says B on it. And they found that basically the keywords are so confusing and the syntax is so confusing that a programming language with randomly generated keywords is almost as good. So this language here on the right is, I mean, it's not really a language, it's something that they made up for this study, but it's called Randomo or whatever. And instead of if, you write colon, and instead of else, you write a comma, and instead of equals, you write backslash, and it's incredibly confusing. But so is Perl. So yeah, don't be like Perl. There's some other fun stories of things going wrong, I guess. So for example, C++ templates are Turing complete. So you could write, any program using just the template part of C++. So you could write like a C++ compiler using C++ templates, which would be dumb, but it's possible. And a consequence of this is that C++ parsing is actually undecidable because you need to be able to parse the templates, which means you need to be able to instantiate the templates, which means you'll need to like run them. So there's actually no such thing as a C++ parser because you have to write an algorithm that does C++ parsing. It's undecidable. So all the C++ parsers only sort of parse C++, which is, I mean, it works, but it's unfortunate. And for another, not to pick on C++ exclusively, but Swift type checking is also undecidable. So again, you can't type check Swift programs. That one requires a more obscure thing. But yeah. On the other hand, if you're going to make a objection to this, you might say, well, C++ and Swift are really popular, so it doesn't actually matter, which is fair. But I think it's at least some evidence that templates are too confusing because this really should not be possible. But anyway, talk about this process of designing programming languages. So basically, you have some subset of these 4 stages of designing programming languages. First stage, these names I just made up, but first stage is exploration, then specification, then implementation, and then evaluation. So depending on who you are and what you're designing the programming language for, you may actually not need to do some of these things. For example, evaluation is something you want to do if you're going to like write a paper about it, but if you're writing your own just fun toy programming language, you probably don't need to worry about that. So next thing we're going to talk about sort of interspersed is the K framework. So the K framework is this program framework for specifying programming languages, type systems, you can do compilers too, I didn't write that, and analysis tools. So basically you write your language, and I'll show some examples of how that works. And then you say how each thing evaluates, and the K framework generates for you a parser, an interpreter, and some analysis tools. So you can, for example, prove that certain programs do certain things. So K framework is great for focusing on just the high-level details of the design of the language without worrying too much about how it's actually implemented. So talk about design, it's sort of the perfect tool. And they're using this toy language called IMP and the K framework to explore some of deep programming language ideas. So IMP is this weird family of imperative languages that get talked a lot about when you're talking about, programming language stuff. There's a lot of variations in how these things work. But basically you have variables, you have expressions with arithmetic like plus and whatnot, and you have loops. And so here's some simple program which computes the sum of the numbers from 0 to 10, I think, if I wrote it right. Yeah, so IMP is basically the simplest programming language that you can have, arguably, other than lambda calculus, which is arguably simpler and more useful, but somewhat harder to understand. So anyway, first stage, exploration. So basically, think about what sort of domain or what sort of problems you want to solve with your language. So for example, you might be writing like some system programming language, or for web programming or simulations or blockchain stuff if you want to be trendy. And basically this tends to be the first stage. Basically you just pick some, like, oh, I want to write a, calculator or something. And you're like, and then you just make up syntax, write a calculator. And at this point, you usually just, whatever you think would be the best possible thing you could write, you just write that and just sort of explore and see what sort of things you can do or you want to do. And then the other thing to think about is doing user studies if it's more of a, if you have the resources to do that, or you can just like, ambush random people and be like, what do you think this program does? Which is actually very helpful. Maybe not totally random people. And then the other thing to think about when you're designing in this very early exploratory stage is this concept of weirdness budget, which basically is, what's the thing that makes your language different? And probably don't pick too many things, because most people don't have a very high tolerance for super weird languages. So for example, Rust has basically only one thing that makes it different from other languages. I mean, overall, it's, solidly designed, but nothing new except for the borrowing, or the borrow checker, which gives it all of its, famed safety and memory management stuff. But other than that, it's basically just like any other language, any other imperative procedural OOP style language. And that seems to be the most effective way to make a language popular, except for being like Apple. And then you can just say, everyone's going to use Swift. But, the other things to think about when you're designing language are sort of where it sits in these various categorization schemes. So, there's paradigms, various paradigms like procedural languages, like C, object-oriented languages like Java, C#, et cetera, most languages, to be honest. Functional languages, logic languages, and a bunch of new things. Or you could even make up your own new paradigm, but that's sort of hard at this point. And lots of languages are multi-paradigm. So that's, something to think about. And then the other thing, two of the other main things is, one is a domain-specific language like LaTeX or SQL or Makefiles that aren't meant, you're not supposed to write like a prime number generator with Makefiles, but you can, but you shouldn't. Versus general purpose languages like C or Python or whatever, you can just, they're supposed to be used to write basically any program. And domain-specific languages actually have a lot of advantages because you can sort of really focus on the one problem you want to solve, and you can do a lot of things that are not practical in a general purpose language, which is why SQL is so good at doing stuff with databases, but you wouldn't write, a web server in SQL. And then the other thing is the statically versus dynamically typed languages. So statically typed, of course, means that the compiler or whatever checks your program to make sure that there are no type errors before you run the program. And dynamically typed basically means that if there are type errors, it'll fail while it's running. Not to give a biased impression of what I think of that, but anyway, specification, next stage. So once you have some idea of this design, then you have to sort of specify the language. So depending on, again, what kind of project you're doing, you may do this informally or formally or some sort of mix of the two. But basically you need to say, syntax, what does the language look like? What can I write? For loops, while loops, are there loops at all? Classes, etc. You specify the type system if you have one. And then the semantics, which is sort of the cool part of what the program actually does. And here's just a random picture from a random page of the Java, the JVM specification, Java virtual machine specification, which, fun fact, uses Prolog to do part of the specification. So Prolog, it's cool. Anyway, so first, one of these subparts for specification is specifying the syntax. And typically, when you're doing formal specifications, you will only specify what's called a core calculus. This is the smallest fragment of your language that is interesting, basically. So you strip out everything that is unnecessary or can be sort of expressed in terms of other constructs that you are keeping. And then the sort of idea is the surface language, which is the thing that people actually write, gets compiled into the core calculus. This isn't always how implementations actually work, but in principle, this is the idea. And then you do proofs, etc., about the core calculus because it's smaller and easier to deal with. And then you say, well, I compile my surface language with the core calculus, so everything works out fine. And then a related but different idea is the idea of an intermediate representation. So if you're familiar with Java bytecode or whatever, that's what Java bytecode is, or LVMIR, or Haskell has several actually. One of them is called core. Different in the sense that typically it's a implementation tool rather than a mathematical model. Yeah, and we'll talk about intermediate representations more when we talk about implementation, but for the moment, I will just say that they exist. So the main way to specify the syntax of a language, formally at least, is via a grammar, which is like this thing that's written down there. That's a grammar of a core calculus of this fragment of Java called featherweight Java, called featherweight because it's so small. Some might argue it's too small because if you sort of see programs written like this, you'll notice that it's not really Java at all. It's this weird functional thing that has classes, but it all fits on one slide, so But basically, what this means is each one of these : equals things is one of the non-terminals of the grammar, one of the things in the language. So L is the class definitions. I don't know why they picked L, but so you have a class with some name, it extends some other class. Those C's don't have to be the same, by the way. And then you have a list of fields and a list of methods. The line over the C and F means there's a list of class field name pairs. So for example, you might have like object X, int Y, etc., just a bunch of those, and then a list of methods. And the methods are also defined in the grammar. So it's a class, which is the return type, the method name, and then the types and names of the arguments, and then a single expression, which is the return value of this method. And then for expressions, you have variables and fields and method calls and etc. And then a program is just a bunch of classes and then a single expression. And then you evaluate this expression with all these class definitions and you get some answer. And that's what the result of the program is. I'm not going to talk too much about featherweight Java, but this is an example of a grammar. And another example of a grammar, this time written, oh, that went off the slide. Oh, well. This time written in the K framework is the syntax for imp. So in imp, we have expressions, which can be integers, ID, which is going to be like variables like X, Y, etc., brackets, just because parentheses are sometimes necessary, plus, minus, and less than or equal to. And then we also have statements, which can be skip, which is like a no-op, it does nothing. And then there's also assignment, if statements, and while loops. And then we have statements, which is either one statement or a statement followed by another statement. Actually, that should be statement followed by statements, because otherwise you could only have 2 statements max, but that's whatever. And then after you have your syntax, you specify the type system. So a type system is, from a practical point of view, it's an algorithm that, given a program or maybe part of a program like a function, it checks if that program is well typed, which basically means that all the types of the function calls and stuff match up. And when you're adding things, you're only adding numbers, and that sort of thing. And these are typically specified, at least if you read programming language papers, by inference rules, which are like things below, which I will briefly talk about, but of course we'll talk about them more when we talk about type theory stuff. So for just a crash course introduction, the part above the line are the premises, the part below the line is the conclusion, the thing to the right of the line is the name, so int, var, or plus. So for example, in this first rule, it just says that if n is in the set of integers, then n is an integer. And the full sort of reading would be if n is in the set of integers, then in the environment gamma, that's the letter to the left of the little plus thing, I guess it's missing the left part, but the little plus thing, it's called turnstile, is gamma, in the environment gamma, n has type int. Then the var rule says in the environment gamma, where x has type t is part of the environment, then x has type t, which seems kind of useless, but you do technically need it. And then the last one is a little bit more, which says that if in whatever environment we're in, gamma, the first expression E1 has type int, and in that same environment, the expression E2 has type int, then when you add the two things, the expression is still of type int. And these rules get more complicated, but I'm not going to go too much into that right now. So one thing that I talk about when you're designing programming languages, not just what type systems are, but why type systems are. So a lot of people love incredibly complicated type systems in programming language circles, like Haskell or dependent types, etc. It turns out that it's actually very hard to show that those things really help write better programs, which is kind of disappointing because I love them too. But basically, there are two purposes of type systems. I think it's documentation and correctness. So documentation is the one that studies actually show type systems help with, and correctness, maybe. But so for example, here, this is from some study where they compared a static language, Java, statically typed language, I think it was Java, and dynamically typed language, which is Groovy, which is basically dynamically typed Java. And they had people do these programming tasks. And basically, so this one on the far left, in the left graph, is how long it took them to do this task using statically typed language and documentation. Then the next one is statically typed with no documentation, then dynamically typed with documentation, and dynamically typed without documentation. So basically, if you have static types and documentation, it took them, what is that, like an hour to do it. Static types, no documentation, took them like 2 hours, and dynamic types, even with documentation, still took, more than 2 hours. And with no documentation, of course, it's even worse. So, well, let me just talk a little about this. So the point of the whole type system thing is that you should sort of focus on what sort of type system actually helps people write better programs. I mean, there's theoretical interestingness with regards to what sort of things you can do with types, but insofar as writing programming languages for like real human people, it's hard to say that there's a benefit to a really complicated type system in terms of actual correctness. And there's other studies that show various documentation benefits of various kinds of type systems, but it's something to keep in mind. So the last thing you need to specify is the semantics of the language. So we're going to do that now in K, the K framework, which is a little bit of an overlap with specification and implementation, because of course, as I said, when you specify the language in K, you get an implementation. So what we're going to do is write rules that say how each one of the constructs in the language is actually evaluated. So we're going to use, a lot of these rules are going to look very simple because the K framework has a lot of things built in that make writing these things much easier. For example, like integers and addition on integers and comparisons on integers. So these rules maybe don't look like they do much, but so the first rule is defining how addition works when both of the things are integers. And all it's saying is basically use the built-in integer addition operation. And the next one is defining what it means for, or how we do integer comparison using less than or equal to. And again, we use the built-in thing. So the way to read one of these rules is that, so each rule starts with rule, then there's some left-hand side and some right-hand side, separated by this arrow symbol, which you can read like rewrites to or evaluates to. And this thing on the left is going to be some syntactic thing in our language, and this is going to be the actual value or result of evaluating that thing. So, what did I say? Oh yeah, so this is just defining addition for integers, but if you recall from earlier, the syntax is more complicated than that. You could have addition of like, x plus 4 or whatever. But the way that this grammar is specified is that it has these additional things called attributes like bracket or strict, which means that in the case of strict, that all of the sub expressions will be evaluated, and then you will evaluate the whole expression itself. So if you have x plus y plus 6 plus 4 or something, it will first evaluate x plus y, then evaluate 6 plus 4, then evaluate x plus y plus 6 plus 4. So that's sort of built-in thing in the K framework that makes it easier to write these things. Okay, maybe I should stop. Are there any questions? Okay, I'm going to take that as a no. But feel free to stop me if there are.
There was a question about logic paradigm. He asked, what example?
Yeah, I was just asking what's an example of a language with a logic paradigm I've not really seen.
Yes.
Or
yeah. So yeah, Prolog is the answer. I don't know if I have anything that. I mean, this here is Prolog. I don't know if you can read that. Basically, how Prolog works is you have these they're called predicates, and then you define sort of in what case the predicates hold, and then you ask the program sort of questions, and it says, oh, this is the things that must happen. That's probably a really vague explanation. Maybe I can actually just show an example of a thing you can do with logic programming, but maybe I'll do that at the end. But I would like to talk about logic programming because I'm a big fan. So I'll probably do that at the end if I have time.
Okay, cool.
Let's see. I think I will have time because I'm talking faster than I planned, which is always what happens. So anyway, we did this. Okay, so the next thing we're talking about is sequencing. So this is what lets us run more than just one thing, which is of course necessary to have any sort of interesting program. And again, maybe this seems like cheating because it's so short, but basically we're just using the built-in stuff that the K framework gives us. So if you recall, we had a skip statement, which was the no-op. So when we evaluate skip, it just evaluates to dot. Dot in the K framework means like done. So this does nothing, it just evaluates to dot. And then if we have one statement followed by another statement, we rewrite it using K's built-in sequencing operator, which is tilde arrowhead. Yeah, it usually looks more like an arrow, but I guess the way it got typeset, the tilde is really high in the line, but whatever. So yeah, when we evaluate first run statement 1, then run statement 2, it just rewrites into statement 1 sequence statement 2, and the K framework will take care of that. So once S1 evaluates to dot, it'll just be taken out and then it'll run statement 2. Okay. So sort of more interesting things are how we handle variable lookup and assignment. So as I was saying before, when we're evaluating these expressions that just have integers, for example, even if it's a bunch of integers, it's really easy because the K framework will just evaluate each side of the addition, and then we evaluate the whole thing once we evaluate each sub-expression. But how do we do things like x plus 1, right, where we have variables? So one way to do this is to use a store, which is basically a map, like a hash map, more or less, that maps the variable name to the value. In this case, all of our variables are integers, but you can imagine having bools and strings and other things. So to do this, we say configuration, we name it store. This is like XML format. I don't know why they chose XML, but whatever, it's fine. Store, and then in it is .map. .map just means empty map. And then, for example, if we want to evaluate a variable, say we're doing something like y equals x, all we do is we match in the store for x, and then we see what value it maps to, which we're calling v, and then x evaluates to v. So the way that this rule actually works is, before, if you recall, these rules were just rule thing evaluates to right-hand side. Now we're working in multiple different cells, as they're called. So we have the store, but we also have the part where the actual program is stored, which is called K for code, I guess, but code with a K. Anyway, so if we're evaluating variable x, it evaluates to v, and the way we get v is by looking at the store. So the triple dots just means other stuff here, and then at some point we encountered this mapping of x to v, and then more other stuff. We don't care about any of that. And that's how we look up in the store. And then when we want to do an actual assignment, it's sort of a similar thing where the current piece of code to be evaluated is x equals v for some integer. And then we rewrite this into dot, meaning that we're done with the statement, and then there's maybe more stuff following. It's kind of unfortunate they chose dot because there's just a lot of dots. But anyway, and then the store cell, we have some environment, and that becomes environment, but now x maps to v. So we've added this value, or changed the value if it's already there. You'll notice that this language doesn't have variable declarations, just assignment, kind of like Python. You can do it either way. This was easier and shorter to fit on one slide, so I did this. Okay. Let's see, yes. So if statements. Turns out if statements are gonna be very easy, again, because of the strict attribute. I'll go back to the syntax brief. Oh. Well, it's cut off, which is very unfortunate for the point I wanna make. But basically what we do is we evaluate this expression that we're conditioning on first, and then we evaluate the rest of the if statement. So the K framework lets us specify that very easily. So all we have to handle are the cases of if the condition evaluates to true and if the condition evaluates to false. So if the condition evaluates to true, then we do the first thing, which was called A in this case. And if it evaluates to false, then we do the second thing, which is called B. So that is it. And hopefully that makes sense. Okay. And then the last thing we have in the language are those while loops, which are not too hard to do if you use sort of this trick, which is how you evaluate a while loop is, so while some condition and then body. Body is a bunch of statements, like x equals y plus 1, et cetera, et cetera. What you do is you rewrite this into if condition, then you run the body, and then you do the while loop again. Otherwise, you just do nothing. So if the condition is true, you run the body, and then essentially just check if the condition is true again. Otherwise, you stop. And this is one way to do while loops. It's not most efficient, but the point isn't really to be efficient right now. Yeah. Hope that makes sense. Okay. And then this is sort of a intersection between specification and implementation, but for sort of a real, I don't want to say commercial grade, but implementation that you might actually use, rather than just for design or verification purposes. Typically, you'll implement your language in some other programming language, and you'll write a compiler or an interpreter or a compiler and a virtual machine, or you'll compile to some other language. So a fairly common thing to do is you can compile whatever language you have to C or to Java or to JavaScript. And that makes your depending on how similar your language is to one of those languages, that can make your life a lot easier because you don't actually have to implement a lot of things that they do in the C compiler. Then the other thing that you can do is you can compile to, for example, Java bytecode, which is the thing that Java compiles to, which is also somewhat easier than compiling to, assembly or machine code because it's a slightly higher level language. And then again, we'll talk about this part more later because there isn't time to talk about all of it right now. There's one point I want to make is that the language specification is more or less independent of the actual implementation. So for example, C is typically compiled, Java is typically compiled, but you could have a C interpreter. It's possible they exist. Maybe it seems a little weird, but there's no reason you can't have that. So rather than, so language is typically, it's not a compiled language or an interpreted language, it's this implementation of the language is interpreted or this implementation is compiled. And the other thing you can do is you can write your language in itself once you have a first version of the compiler, which is usually sort of considered like a good test of is your language good enough, is if you can implement it in itself. That's called self-hosting. We can talk about that when we do implementation, but yeah. Okay. And then the final step is evaluation. So now that you have a language, is your language good? So this is something you only have to worry about basically if you're going to write a paper or something, or if you want to like convince people that they should use your language. But if you don't care about that, then don't do it. Yeah. So, but I'm going to talk briefly about sort of the 4 biggest evaluation methods or most widely used evaluation methods for proving that you should use my programming language. So one of them is case studies or maybe small examples, which basically you take some program, say you're writing a like system language, then you write a program that does, I don't know, like thread scheduling or something. And then you say, look, my programming language makes writing, the scheduler super easy, so you should use my language. Which is sort of a good start, but not really empirically like, oh, my language is actually better. It's just like, doesn't this seem nicer? But it's a good sort of first step. The other thing you can do is you can do user studies. This is sort of wasn't very popular until recently, but now people are realizing that, the people who write programs are like people. So you can study them using HCI methods and determine which languages are actually easier to use. So you can do things like, get a bunch of people, have them both write programs in, or have them write programs in both your language and, what's some other language, usually the like standard language of the domain. So for example, if you're doing like system programming or something, maybe you would have the people write code in your language and in C. And then you basically say, look, they made mistakes in C and they didn't make these mistakes in my language, so my language is better, which is useful. And then the other thing, depending on the domain you're targeting, is you might want to profile your language, either the compiler or the interpreter or the compiled programs, and say, look, I'm faster than C or faster than, whatever you care about. And the final thing is doing formal proofs. So this is something, this is sort of the, I don't want to say it's the hardest, but it is like a lot of effort. But you can prove, type safety, or you can prove other properties of your language. Like, for example, if you're doing Rust or something, you might prove, oh, you never have memory leaks if you use like the safe part of the language. And that gives you sort of the highest possible assurance that your language sort of design is correct and shows, unambiguously that your language has this advantage. It's not just, my language looks nice, it's my language is actually good. But of course, that takes a lot of time, and depending on the language, you may have, hundreds of little cases in your proof, which is, of course, why, as I was saying earlier, you make the core calculus, which is relatively small. Yeah, so I think, yeah, that's all I have. Again, I think I talked maybe a little faster than I was originally intending, but yeah, are there any questions? I should check the chat. I don't have it
Oh,
open.
wait, yeah. Are we gonna be talking more in detail about like K and stuff? Because I guess I get kind of roughly the syntax and stuff like that, but
yeah. Yeah, so the plan is to either have, I don't know, probably not. Okay, so the plan is either have one more like lecture-y thing, and then next time after would do like a workshop where like, you know, we like write a thing in K and, you know, everyone sort of follows along and whatever. So hopefully that will address the question of, you know, how do you actually use K? We'll probably do that next time, I guess.
okay, cool.
Yeah. Yeah, and then if there's other questions, but feel free to ask. I will try to do a brief prologue demo to show some cool stuff that you can do. Okay, I will do that. One second. What? Okay. Can you also see my screen?
Yeah.
Yeah, just the slides, I guess.
Oh, okay. I want to share the whole thing. One sec. Okay. Can you see the terminal now? Okay.
Yeah.
It's a little bigger. Okay. So let's see. Yeah. So logic programming. Let me open a separate file. Okay. So as I was saying before, the idea behind logic programming is basically you define these relationships, these predicates, and conditions in which, you know, when they hold, and then you ask the program questions and it answers them for you using the things you've defined. So for example, I can first define some facts about the world. So I'm going to define the age. My age is 21. I don't know how old Eric is, but I'm going to say he's 22, so he's not the same age as me. I mean, you can tell me if you want, but it doesn't really matter. And I'll say age of Colin is like 19 or something. I don't know. Anyway, the point is that they're all different. So now if I load this program in Prolog, I can ask, you know, what is the, you know, the age of Reed is X, and it will say 21. And I can say the age of Eric is what, and it says 22. So this is sort of a very basic, you know, facts about the world sort of thing. But you can ask much more interesting questions. I'm going to make these smaller so you can see both. You ask much more interesting questions like, well, let's start with something simple, which is, you know, who is 21, for example, and then it will tell me Reed is 21. So I can use the relationships in sort of both directions. And then I can also say, you know, I can have it just enumerate all the possibilities. I can say age X and Y. So it says, you know, Reed is 21, Eric is 22, Colin is 19. And then what you can do is you can write rules using these facts. So I can say, you know, when is one person older than another person? So this is person A and this is person B. So person A is older than person B when person A is n years old, person B is m years old, and n is greater than m. Maybe greater than or equal to, but I'll just say greater than. And then I'll reload the file. And now I can say, is Eric Eric older than Reed? And it says true. I can do other things. I can say, is Reed older than Eric? And it will say false. Okay, but then I can also say, you know, Eric is older than who? And it will say Eric is older than Reed and Eric is older than Colin. And there's no other answers. So this is sort of how you use these rules to make sort of do more interesting things, which is much more powerful than just what I'm showing here. The sort of classic example is writing a Sudoku program. I don't know if I want to do that, right now, but what other things can you do? Yeah, I'll just do like one more example maybe, unless, well, we'll see. So one thing that we have in Prolog is there's lists. So you can have like x's like these 3 numbers or whatever. And then there's a function or relation called append, which takes 2 lists like this and gives you a new list. So if I append 1, 2, 3 and 4, 5, 6, I get 1, 2, 3, 4, 5, 6, right? Which is pretty straightforward. But again, just like these other things, you can use them in sort of all sorts of directions. So I can say, for example, what list, when I append it to 1, 2, 3, gives me 1, 2, 3, 4, 5, 6. And it will tell me you have to do the list 4, 5, 6. Yeah, and then you can do sort of, what are all the lists that when I append them, I get 1, 2, 3, and it'll just give me all the different possible answers to that question. Which is essentially when you combine these things, you get a lot of really powerful programs that you can explore your problem in a very interesting way. Yeah.
Okay, nice. Oh, that seems pretty cool, actually.
Yes.
I guess even though I don't know about any like more complex programs, this seems like interesting enough. You can kind of see how you might use this too.
Yeah, I like it a lot. I also wrote my website using Prolog, which is not sort of what Prolog is ideally used for, but it worked pretty well. And a few other random programs using Prolog. I would definitely recommend checking it out at least because it is cool, even if you don't end up actually using it to write things.
Okay, nice. Wait, does Prolog have like website like display support and stuff?
Yeah, yeah. You can write servers in Prolog. I mean, yeah, I didn't write like my own like HTML libraries or whatever. I just used what they have.
Okay, gotcha.
Yeah. Yeah, so that was what I had planned. I'd have to just give demos of other cool programming languages, but if anyone has questions, I can answer. Otherwise, yeah. I'll stop the recording at this point.